Hello everyone, this is Jun Sun. In this video, I will discuss the fit of my best performing class field for the practice machine learning and for final hacks, and the specific actions I took to improve performance and access or improve model fit. The task is a binary classification problem, predicting diabetes binary, where 0 means no diabetes and 1 means pre-diabetes or diabetes. The dataset has about 110,000 survey response and 21 features, and it is class imbalance. So the competition evaluates performance using the F1 score, which balances prediction and the recall and is more appropriate than accuracy when the positive class is less frequent. My final cargo submission score was 0.74, and my final submission file was generated from my XGBoost pipeline. I began by loading the training and test files, splitting the training data into features X and targeted Y, and the preserving the test ID column only for submission to ensure fair and consistent model comparison. I used a stratified training validation split, so the class appropriation stay consistent across the split. I also built an on-field evaluation routine. Instead of using a fixed 0.5 cutoff, I evaluate models based on predicted probability and performed a threshold search across a grid to find the threshold that maximizes validation F1. Alongside F1, I tracked the prediction, recall, ROC, AUC, and the confusion matrix, so I could interpret how each modeling changing affect false positive and false negatives, not just a headline score. My baseline model was a logistic regression pipeline with standard scalar using L2 regularization and class weight balanced to explicitly address class imbalance. I used the logistic regression first because it is stable, interpretable, and fast, and it provides a reliable benchmark that helps validate the data pipeline and confirm that there's a signal in the features. This baseline also made it easier to measure the incremental value of more complex nonlinear models later, because I could directly compare validation metrics under the same split and the same threshold optimization procedure. After establishing the baseline, I moved to gradient boosting model because they capture nonlinear relationships and interactions more effectively. I trained LightGB. I'm using scale pulse weight computed as the ratio of negative to positive examples to handle imbalance at the lowest level. For model fit, an important tool I used was early stopping on the validation set by monitoring validation performance during training and stopping when it no longer improved. I reduced the risk of overfitting when using a large number of boosting runs. Then experimented with stronger LightGBM configuration mode estimators with a smaller learning rate and aided regularization and simply controls such as reg alpha, reg lambda, subsample, and column sampling to increase model capacity while maintaining generalization. One of the most meaningful performance improvements came from features engineering. Rather than relying only on hyperparameters tuning, I created additional features with clear health-related intuition and applied them constantly to train validation and test data. Examples include a composite health score combining general mental and physical health indicators, a lifestyle risk score combining high blood pressure, high child smoking, and heavy alcohol consumption, and interaction features like cardio risk and multiple risk that combine related variables. I also used interactions like age BMI to capture combined effect of age and BMI. After adding these engineered features, I retrained the boosting model and reran the same threshold optimization and metric reporting to quantify whether the change improved F1 and how they shift precision versus recall. And because the dataset is imbalanced and the courses coverage include balanced versus imbalanced strategies. I also test a resembling approach using SMOT. I applied SMOT to the training portion of the split to synthetic additional binary class examples, and then retrained a model such as logistic regression on the balanced train set while evaluating on the original validation distribution. This experiment helped me understand whether oversampling could improve recall and overall F1. At the same time, I treated SMOT as a controlled comparison rather than a quantitative solution because synthetic samples can sometimes create unrealistic decision boundary. In my results, the most reliable gains come from imbalance while boosting plus thresholding rather than relying entirely on oversampling. To push performance further, I explored ensembling. One approach was soft voting, where I combined predictive probability from models like logistic regression and feature engineered light GBM through a weighted average, aiming to blend linear stability with nonlinear power. I also experimented with stacking using a logistic regression trained on the base model's probability outputs. A key fit consideration here is avoiding training on the validation set in a way that overfitted it. So I implemented at out-of-field stacking method using stress field KF-fold to predict out-of-field prediction for the base model. The produce a cleaner training signal for the MAT model and improve generalization compared to nav staking and on a single holdout. Overall, my best performing standalone classifier was XGBoost. Training on the engineered feature set, I handled imbalance using scale pulse weight and controlled fit using regularization parameters such as reg alpha and reg lambda, along with subsampling and column sampling to reduce variance. I also used a large number of estimates with a smaller learning rate, which typically improves fit by learning more gradually and preventing overly aggressive boosting. Importantly, I did not treat the classifier output as final at a 0.5 cutoff. Since the evaluation metric is F1, the optimal decision threshold is often not 0.5 under imbalance. So I performed a threshold search and then refined it with a more fine-grained search around the promising regions. For the final submission, I used a threshold of 0.52 to convert probability into 0 and 1 predictions, which aligned well with the F1 objective. The pipeline produced my final cargo score of 0.74. In terms of assessing and improving fit, I used several tools and diagonals. First, I used the start field holdout validation split to evaluate generalization constantly. Second, I use explicit fit control mechanisms, including early stopping in light GBM and the regularization pass sampling in both light GBM and XGBoost. Third, I evaluated multiple metrics, F1, precision, recall, AUC, and the confusion metrics to understand whether performing gains were driven by catching more position or reducing false positives, and to ensure improvements were not combined from an unhealthy trade-off. I also performed exploratory checks such as class distribution review, correlation analysis, PC evaluation for a rough separability check, and model-based feature importance to verify that the model was learning possible pattern rather than noises. To conclusion, my final workflow was to select the best performing configuration XGBoost with engineered features, training it on the full training data general probability for the test set, and apply the cargo optimized threshold of 0.52 to produce the final submission file. The biggest drivers of improved performance were imbalance aware boosting, hypersys driven feature engineering, and metric aligned threshold optimization, where the biggest drivers of good fit were early spotting, additional regularization, subsampling, and out-of-field evaluation for stacking. If I had additional time, I would further systematize cross-validation, hyperparameter tuning, and explore collaboration and more advanced assembly. But within the time constraints, these steps giving a strong, well-justified model with a final cargo. Thank you for your watching.